Hello, welcome to today's class. In today's class, we will talk about the 8 puzzle and heuristic functions to solve the 8 puzzle problem. The 8 puzzle problem consists of a 3 by 3 board with 8 numbered tiles and a blank space. The diagram here shows one possible configuration for the 8 puzzle problem. It shows that we have a 3 by 3 board and we have the tiles from 1 to 3 up to 8, and we also have a blank space at the center. A tile adjacent to the blank space can be slid into the blank space. For example, 6 can be moved into the blank space, or 5 may be moved into the blank space, or 2 may be moved to the blank space, or 3 may be moved to the blank space. The objective is to reach a specified goal state. For example, this may be a goal state. So, starting at a given start state, the goal is to reach the goal state by moving the slides into the blank space. By making different moves, we want to reach the goal state starting at the start state. So now talking about the possible actions in the 8 puzzle problem, we said that a tile adjacent to the blank space can slide into the blank space. The movement of the adjacent tile can also be thought as the movement of the blank space in the left direction, or the right direction, or the upward direction, or the downward direction. This is explained below. Consider this configuration where the blank space is at the middle. Now we can move the blank space upward, and if we move the blank space upward, this would be the new configuration of the board. The blank space was here and it moved up. So actually 2 came down to fill up the blank space, and the blank space has moved upward. Or the blank space may be moved downward. If we make this move, this would be the new configuration of the board. If we perform the action where the blank space moves to the left, then this would be the new configuration of the board. And if we move the blank space to the right, then this would be the new configuration of the board. So in this particular state, 4 different actions can be performed, and the resultant configuration for each of the move is shown in the diagram. Next, consider this new configuration where the blank space is in one of the edge. When the blank space is in one of the edge, only 3 different actions are possible. For example, in this case, the blank space can either move upward, or it may move downward, or it may move to the left. Since it is at the edge, it cannot move to the right in this particular configuration. The diagram also shows the new configuration for each of the action. So when we perform the action, move the blank space up, this would be the resultant configuration. If we perform the action move the blank space down, then this would be the new configuration. And if you perform the action move the blank space to the left, then the blank space would come here and 6 would move into the blank space. Next case could be that the blank space is in one of the four corners. When the blank space is in one of the four corners, then only two different actions can be performed. In this particular configuration, the blank space can either move downward or it may move to the left. When we move the blank space downward, this would be new configuration, and when we move the blank space to the left, this would be the new configuration. So what we saw is that when the blank space is at the middle, then four actions are possible, and when the blank space is at one of the edge, three actions are possible, and the blank space is at one of the corner, two actions are possible. So for some states we can perform four actions, so that state will have four different successors. For some states we can perform three actions, and for those states we will have three successors each, and for some states we can perform only two actions, and those states will have two successors each. So now in average, given a node, they will have about three successors. So the branching factor for the state space is about 3. Now the average solution for a randomly generated 8 puzzle instance is about 22 steps. So given any starting state, we may need to make 22 moves to reach the goal state. From some state we may need to make more than 22 steps. From some states we may need to make less than 22 steps, but in average we need to make about 22 steps to reach the goal state from a randomly generated initial state. So an exhaustive tree search to depth 22 would look at about 3 to the power 22, which is approximately equal to 3.1 into 10 to the power 10 states. That's because the branching factor is 3. So at the depth of 22, there would be 3 to the power 22 nodes or states. Now graph search would look at about 9 factorial divided by 2, that's 1,81,440. So in graph search we don't allow repeated nodes, hence compared to the tree search we will need to look at less number of nodes, and for the 8 puzzle game, in case of a graph search we may need to generate 1,81,440 states. This is not a very large number, and the uninformed algorithms may be able to solve the problem, but if we go for the 15 puzzle instead of the 8 puzzle problem, then even for graph search we may need to look at about 10 to the power 13 states, and uninformed search may take a long time to find a solution for the 15 puzzle problem. So we need to look at informed search, and to be able to use informed search for the 8 puzzle problem we need to come up with some heuristic functions, and here we will discuss two possible heuristic functions that we can use for the 8 puzzle problem. The first heuristic function is the number of misplaced tiles. So if we consider this given start state and the corresponding given goal state, we will see that each of the 8 tiles are misplaced. For example, tile number 7 in the start state is at the first row first column, whereas the actual position of tile 7 in the goal state is third row second column. So tile number 7 is not at the correct place. Similarly, the other tiles are also not at the correct position. Hence all the 8 tiles are misplaced, and hence h1 for the given start state is equal to 8. So 8 because all the 8 tiles are misplaced. A second possible heuristic function for the 8 puzzle problem is the Manhattan distance. So Manhattan distance is the sum of the horizontal and the vertical distances of the tiles from the goal positions. So again, let us look at this given start state and the corresponding goal state. So if you consider tile number 7, in the start state it is present in the first row first column, whereas in the goal state the position is third row second column. So we need to move tile number 7 to its correct position, and to that we have to move the tile vertically twice and then horizontally one more time. So in total the number of moves vertically is equal to 2 and the number of moves horizontally is equal to 1. So Manhattan distance for tile number 7 is 2 plus 1, which is equal to 3. Similarly, for tile number 2, its position in the start state is first row second column, whereas in the goal state tile number 2 is present in first row third column. So to move to its correct position, for tile number 2 we need to make one move horizontally. So the Manhattan distance for tile 2 is 1. Similarly for tile 1, in the start state it is present in the third row third column, whereas its correct position is first row second column, and hence to move tile 1 to its correct position we have to make 2 moves in the vertical direction and 1 move on the horizontal direction, and hence the Manhattan distance for tile 1 is 3. For tile 3 similarly, we need to make 2 moves to take tile 3 to its correct position, and hence the Manhattan distance is 2. For 4, we need to move vertically once and another move horizontally, so Manhattan distance for tile 4 is 2. For tile 5 we have to make 2 horizontal moves, and hence the Manhattan distance for tile 5 is 2. For 6, we have to make 1 move vertically and 2 move horizontally, so Manhattan distance for tile 6 is 3. And for tile 8, so here is a typo actually, so for tile 8 again it is 2 moves. So the Manhattan distance for the given start state is the sum of all these Manhattan distances, and hence the h2 for the given start state is equal to 18. In one of the earlier class we have seen that the heuristic function needs to be non-negative, and with the constraint that if n is the goal node, then h of n should be equal to 0. Now the two heuristic functions that we discussed today satisfies these conditions. Of course they are non-negative because we are counting the number of misplaced tiles or the number of moves that we have to make horizontally and then vertically. Hence the two functions are non-negative, and also if we are already in the goal state, then the number of misplaced tiles will be 0, and of course the Manhattan distance will also be 0. So the two heuristic functions that we discussed today do satisfy these conditions. With that I would like to end today's class. We'll meet again in the next class. We'll talk about consistent and admissible heuristics. So bye for today. We'll meet again in the next class. Thank you. Bye.